Nat 405 Physics, Vectors and Scalars, Speed and Velocity. The key areas we will cover today are recapping the definitions of vector and scalar, the definition of speed, how to calculate average speed, instantaneous speed, the definition of velocity, and how to calculate average velocity. Vectors and scalars. Remembering back from the past lesson, a scalar quantity is fully defined by magnitude only, where magnitude is the size of something. A vector quantity is fully defined by using both a magnitude and a direction. Speed. Speed is defined as the distance travelled per unit time. Speed is an example of a scalar quantity. For all speed calculations, we use the equation d equals vt, where d is distance measured in meters, v is speed measured in meters per second, and t is time measured in seconds. So distance equals speed times time. Triangles can also help with this equation. Looking at our first triangle, if we cover up the d, we get d equals v times t. Looking at the second, if we cover up the v instead, we're going to get v equals d over t, or d divided by t. And the third, if we cover up t instead, we're going to get t equals d over v, or d divided by v. The term average speed is often useful for calculations involving long journeys. For average speed calculations, the equation is written as d equals v bar t, where d is the distance measured in meters again, v bar is average speed measured in meters per second, and t is time measured in seconds. So you can see distance and time have stayed exactly the same, but the speed now has a line across the top of it. This just denotes that it's average speed. That's all that line means. Example 1. A car travels a distance of 35 meters in a time of 5 seconds. Calculate the average speed of the car. Like with all equation questions, we want to first write down what we know and what we want to work out. So we want to work out the average speed of the car. So v bar equals our question mark. We have a distance of 35 meters in a time of 5 seconds. So we can add both of those in. D equals 35 meters and t equals 5 seconds. Now we want to use our equation. D equals v bar t. 35 equals our average speed multiplied by 5. And now we want to rearrange this, taking our 5 across to the other side. So it turns into average speed equals 35 divided by 5. This gives us a final answer of 7 meters per second. Example 2. A cyclist has an average speed of 8.5 meters per second and travels for 8 seconds. Calculate the distance travelled by the cyclist during this time. Again, we want to write down on the left-hand side what we know and what we want to work out. So we have v bar, we have d, and we have t. Our average speed is 8.5 meters per second. That's given in our question. And we're also given the time, so it travels for 8 seconds. The distance is what we want to work out. Using our equation, d equals v bar t, we've got d equals 8.5 multiplied by 8. We don't need to do any rearranging here. We just need to multiply the two together to get 68. And because it's the distance, that's measured in meters. Never forget your units. Example 3. A vehicle has an average speed of 23 meters per second when it travels for 345 meters. Calculate the time taken by the vehicle for the 345 meter journey. Like before, we want to write down what we know and what we want to work out. So v bar, d, and t. We've been given the average speed, which is 23 meters per second. We've been given a distance, so that's the 345 meters. And this time we want to calculate the time taken by the vehicle for the 345 meter journey. Again, using the same equation as before, we've got d equals v bar t. We want to fill in our numbers, so 345 equals 23 multiplied by our time. Rearranging this gets us to 345 divided by 23, Popping that into a calculator, we get to 15. So our time is 15 seconds. What you can do now is take a moment to pause this slide and have a go at these extra questions here. So in some of them you're given the distance and the time and you need to work out your speed, and in others you're given different values and there's one missing. So pause now to complete the table. Here is the table to check your answers. The term instantaneous speed is defined as the speed at a particular instant in an object's journey. This means that very short time intervals are used in instantaneous speed calculations. To measure these very short time intervals, a device called a light gate can be used along with a timing app. Carry out practical work or research to find out how a light gate and a timing app can help calculate instantaneous speed. Investigate instantaneous speed using the following apparatus. So here we have a diagram. At the top we have a trolley with a piece of card on top, and that is on a ramp. At the bottom of the ramp we have a light gate set up, and it's connected to an electronic timer. We also have a stop clock and a ruler. What we're going to do is let the trolley go at the top of the ramp and allow it to roll down the ramp. So it's going to follow this path just here, and it's going to go through the light gate. The card itself will travel through the light gate, blocking this light. When the front of the card, just here, goes through the light gate, it's going to block that light and the electronic timer will turn on. When the end of the card, so this back piece just here, completely goes through the light gate, the light will flow again and the electronic timer will turn off. What this will give you is the time taken for the card to pass through the light gate, so the time taken for the trolley to pass through the light gate. We also have a ruler just here, and we will use this to measure the length of the card. A possible set of data is shown below. The length of the card could be 10 centimeters, and the time on the electronic timer could be 0.185 seconds. As you can see, this is a very short time. The equation for instantaneous speed is instantaneous speed equals the length of the card divided by the time on the electronic timer. You can see just here that the length of the card is equivalent to distance. Time on the electronic timer is obviously equivalent to time. And the instantaneous speed is equivalent to just speed. And this is the same as our speed distance time equation. So speed equals distance divided by time. What we can do is we can work out the result we get from this. So our speed is going to be equal to the length of the card, that's 10 centimeters, but we know this has to be in meters. 10 centimeters in meters is 0.1 meters. And we're dividing this by the time of the electronic timer, which is 0.185 seconds. 0.1 divided by 0.185 is equal to 0.5405, and it just carries on going like that. So V equals 0.540 and so on. We can round this to two significant figures as 0.54 meters per second. So this is the instantaneous speed of the trolley at the light gate. Velocity. Velocity is a vector quantity, and it has the symbol v. Velocity can be calculated using the equation velocity equals displacement divided by time. You can see this is very similar to our speed distance time equation, but instead of distance we have displacement, and instead of speed we have velocity. So it's the vector equivalent of speed. An answer to a velocity calculation must state the direction of motion. This is because it's a vector, so it has to include a magnitude and a direction. Triangles can also help with this equation. If we want to work out the displacement, we would cover up the s and find out that displacement equals velocity times time. If we want to find out for the velocity, we cover up the v and find out velocity equals displacement divided by time. And if we want to work out the time, we cover up the t and find that t equals displacement divided by velocity. The term average velocity is often useful for calculations involving long journeys. For average velocity calculations, the equation is written as s equals v bar t, and you can see this is really similar to our average speed equation. We have S equaling displacement, measured in meters. V bar is average velocity, measured in meters per second. And T is time, measured in seconds. Example 1. A car travels 30 kilometers due north in 30 minutes. Calculate the car's velocity. Just like we've been doing in previous questions, we want to write down the values that we know and the values we want to calculate. In this question, it's asking us to calculate the car's velocity, so V equals a question mark. We've got a displacement just here of 30 kilometers due north. So S equals 30 kilometers north. We also have a time, and that's 30 minutes. One thing you need to notice in this question is that displacement should be given in meters and time should be given in seconds. So our S is actually 30 kilometers times by 1,000 to give us in meters, so 30,000 meters. And the time should be 30 minutes multiplied by 60 to get it into seconds, which gives us 1,800 seconds. Now we have both of these values, we can go ahead and calculate the velocity. So displacement equals velocity times time. 30,000 equals V times by 1,800. Rearranging this, we get to velocity is 30,000 divided by 1,800. And popping that into a calculator, it gives us 16.666. This 6 is recurring, so it just carries on. And we can round this. Before we round it, we want to have a think about how many significant figures we can round it to. So working across to the right-hand side here, can you remember the rule for the number of significant figures we need to round to? If you can't, the rule is you can round between 1 less up to 2 more significant figures than the minimum number given in the question. So let's have a look at our significant figures in the question. Just here we have 30 kilometers. This has 1 significant figure. We also have 30 minutes. This is also 1 significant figure. So the minimum in the question is 1. We can round between 1 less up to 2 more significant figures. As you can see in my little sentence, I missed out the 2 here. Let's add that in. 1 less to 2 more significant figures. We can't round 1 less than 1 because that would be 0. That wouldn't make sense. So our minimum number we can round to is 1. 2 more than 1 is 3. So we can round our answer from 1 to 3 significant figures. Having a look at our answer, it's 16.6 recurring, so we could round this to 20, we could round it to 17, or we could round it to 16.7 meters per second. And remember, because this is a velocity, we need to put direction as well. And the direction we were given in the question was due north, so we have to include this as well. So our final answer is 16.7 meters per second due north. Example 2. A cyclist has an average velocity of 6.5 meters per second at 225 and travels for 8 seconds. Calculate the cyclist's displacement during this time. Remember, this 225 is our angle from north. So looking at a compass, our north is up the way just here, and we have east, south and west. 225 would be somewhere between south and west, down in this direction. Let's calculate the cyclist's displacement. So first of all, we want to write down all of the values we have. So our average velocity, so V bar, is 6.5 meters per second at 225 degrees from north. The displacement, S, is our question mark, and the time is 8 seconds. We don't need to do anything to our 8 seconds or our 6.5 meters per second. They're already in the correct units, so we can move straight on to our equation. S equals V bar T, so S equals 6.5 multiplied by 8. 6.5 multiplied by 8 is 52. So our displacement is 52 meters And remember, because it's a vector, we need to include a direction, and we've been given the direction in the question, so we say 52 meters at 225. Example 3. The magnitude of a vehicle's average velocity is 13 meters per second when it travels for 3.9 kilometers due west. Calculate the time taken by the vehicle for this journey. Same as before, we want to write down what we know and what we don't know. So our average velocity, v bar, is 13 meters per second. And it's saying when it travels for 3.9 kilometers due west. So we can say this velocity, because it's a vector, is due west. And we also know the displacement will be due west as well. We can see the displacement is 3.9 kilometers. The time is what we want to work out, so t equals question mark. Using our equation, s equals v bar t, we can pop in our numbers. So 13 equals, having a look at, oh, I've put the numbers in the wrong way around, haven't I? Looking at our displacement, before we start putting some numbers in, we've got 3.9 kilometers. This needs to be in meters. So 3.9 times by 1,000 gives us 3,900 meters. That can go into our equation. 3,900 equals 13 multiplied by our time. So we want to rearrange this and do 3,900 divided by 13, which is our time, and that is an answer of 300. And remember, this is time, it's given in seconds. Time is not a vector quantity, time is a scalar, so we can leave our answer as this. The time is 300 seconds. What you can do now is complete the following table. So calculate the missing values in each of the rows. Pause to give yourself time to do this. Here are the answers for you to check yours against. Pause now if you want to do this. Here are some review questions for us to look at. Question 1. A car travels 50 kilometers due north and then 30 kilometers due south. The whole journey lasted for 2 hours. Calculate A, the distance travelled, B, the average speed in kilometers per hour, C, the displacement, and D, the average velocity. First of all, let's look at part A. We want to calculate the total distance travelled. We know that the total distance is just a simple addition, and we can see in the question, the car travels 50 kilometers and then 30 kilometers. So all we're doing is adding 50 kilometers and 30 kilometers to get the distance. This gives us 80 kilometers. Let's look at part B. The average speed in kilometers per hour. Notice it's not meters per second we're doing this in, this is kilometers per hour. So when we're writing out all of our values, we need to make sure our distances are in kilometers and our time is in hours. So our average speed, v bar, is our question mark. Our distance is 80 kilometers. And our time is 2 hours. We can see that up here. Now let's use our equation to work out our final answer. D equals v bar t. So 80 is equal to our average speed multiplied by 2. So our average speed is equal to 80 divided by 2. So we get an average speed of 40. Remember the units, it's kilometers per hour. I'm just going to remove A and B for now to give us space to do questions C and D. So question C asks us to find the displacement. We know that when finding displacement, remembering back to a previous lesson, we have to work out the total distance travelled between the start and end points. So drawing a little diagram, what this looks like is our start point here, we're travelling 50 kilometres north. In fact, if I put the number across to the left-hand side, it'll be easier to visualise. This is 50 kilometres altogether. Then grabbing a different colour, we're going 30 kilometres south. So I'm going to overlay this on top to help you visualise it. So 50 kilometers north, then 30 kilometers south. What we have to look at is the difference between these two. So we've got our start point, as you can see, and then we have our end point just here. This distance just here is our displacement. So what we can do is we can take 50 and minus 30. We travel 50, travel 30 back, and in total we get 20 kilometers. And remember, displacement is a vector, so we need a direction on here. We are 20 kilometers further north than we originally were. So 20 kilometers north. Part D is the average velocity we're looking for. So the average velocity is a very similar equation, if you can remember, to the speed equation. But instead we've got our average velocity, v bar, we have displacement, and we have time. So we want a question mark for our average velocity. Our displacement was 20 kilometers this time. And our time was the same 2 hours as before. The question does not specify giving it in meters per second or kilometers per hour, but previously we worked out the average speed in kilometers per hour, so again let's work out the average velocity in kilometers per hour. Using our equation, S equals v bar t, we have 20 equals v bar multiplied by 2. Rearranging this, our average velocity is 20 divided by 2. So our average velocity is 10, and remember the units, it's kilometers per hour. And also, because velocity, or average velocity, is a vector, we need a direction here. The same as our displacement, it's going to be north. So 10 kilometers per hour north. Question 2. A student travels home by walking 200 meters due north, then 150 meters due west. The whole journey lasted for 10 minutes. Calculate A, the distance travelled, B, the average speed, C, the displacement, and D, the average velocity. Again, let's go for distance first. So we know the distance is a simple addition. So the distance is going to be equal to this 200 meters, add on the 150 meters. So in total, our distance is 350 meters. For part B, we're working out the average speed, so v bar equals a question mark. The distance is what we just calculated, that's the 350 meters. And our time, having a look in the question, it was 10 minutes. Remember, the 10 minutes has to be in seconds, so we take the 10 times it by 60, we get 600 seconds. Now we have our distance and time, we want to calculate our average speed. So distance equals average speed multiplied by time. 350 equals v bar times by 600. Rearranging this, we get our average speed equals 350 over 600. I'm going to pop it into a calculator just now. And what we get is 0.583. And this just keeps on going, 333 and so on. We can round this to having a look at our significant figures again, just like previous question. Let's give ourselves a little bit of space up at the top here. Remember the rule from before, it was 1 less up to 2 more significant figures than the minimum number given in the question. Having a look at the question, we've got 2 significant figures here. Oh, no, I'm wrong there. I was looking at the other one. We've got 1 significant figure just there. It's 200. 1 significant figure there. We've got 2 significant figures here, and we've got 1 significant figure here. So the minimum is 1. We can't go 1 less than 1, so our minimum has to be 1. And 2 more than this is 3. So the number of significant figures we can round to is between 1 and 3. This means our answer can be rounded to 0.6, 0.58, or 0.583. I'm going to round mine to 0.58 meters per second. Like before, I've removed parts A and B, so we have space to do parts C and D. Looking at part C, we want to work out the displacement. So to do this, we want to draw ourselves a little diagram. So the student travels home by walking 200 meters due north. So if we start here, they're going 200 meters north and then 150 meters west. If we want to calculate the displacement, this is the difference between our start and end point. So remembering back to our previous lesson, as the crow flies from the start to the end point. And I'll draw that on as a dotted line just here. We're going to label this as S, for our symbol for displacement. To find this, we want to use Pythagoras. So S squared equals 150 squared plus 200 squared. The right-hand side of our equation, 150 squared plus 200 squared, is 62,500 altogether. And so taking the square root of this gives us a displacement of 250, a nice round number just there. And it has to be consistent units as before, so 250 meters. But this isn't our final displacement because this is just a number. We need an angle as well. So our angle is just here because it always has to be from the start point. And we want to use trigonometry to find this out. So labeling our sides, we've got our opposite, we've got our adjacent, and we've got our hypotenuse. If this is all a little bit unclear to you, I recommend going back to the first lesson where we looked at distance and displacement and recapping more on trigonometry. But follow along here and see if you get a hang of it. So we have SOHCAHTOA. We want to tick the values we were given in the question, so our opposite and our adjacent. So we want to use tan for this question. Tan of our angle is equal to opposite over adjacent. So tan of theta is equal to, the opposite is 150 divided by our adjacent, which is 200. And now we want to rearrange this. So theta is the inverse of tan of 150 over 200. To find that function on your calculator, you want to press Shift and tan. It'll take you to the inverse of tan. And then in the brackets, you want 150 divided by 200. And that gets you to an answer of theta equals 36.8698 and so on. We can round this to a whole number as 37 degrees. But this still isn't our final answer just here, because we can't just give this as 37 degrees because that doesn't provide a reference point. We need to show it as a number relating to north. So clockwise from north. Remember our directions, north is always upwards on our page. So what our angle looks like is this. That's mimicking our diagram across to the left, but we need this angle just here. What we can do is we can remember that the full circle is 360. And if we take away our angle just here, so 360 take away theta is going to give us our final answer. So that's 360 take away 37. That gives us an angle of 323. So our final answer for displacement is 250 meters at 323 degrees from north. Moving on to our final part of the question, we want to work out the average velocity. So we want to use our equation for average velocity, so v bar, s and t. Writing down the values we don't know and don't know, we want a question mark next to our average velocity. Our displacement, remember we just calculated that in the last question, that was 250 meters at 323. And our time is the same time as we've previously been using, that's 10 minutes. And if you remember, time needs to be in seconds, so we do 10 times 6t, 10 times 60, which is 600 seconds. Using our equation, s equals v bar t, we want to pop our numbers in, so 250 equals v bar times by 600. Rearranging this, we get our average velocity equals 250 divided by 600. Just popping that into my calculator just now, what we get to is 0.416 recurring. And we can round this to 0.42 meters per second. And remember, because it's average velocity, it's a vector, it needs a direction, and it's going to be the same direction as our displacement. So again, it's at 323 just there. And that's our final answer.